Hello, my name is Georgopoulou and I come from the Hellenic Center of Marine Research in Crete, Greece. And today I'm going to present you a study that is part of the Horizon 2020 iFishIENCi project and is about a methodology that we have developed for the tracking and analysis of movement of European SEABASS in RAS systems. Here you can see the structure of my presentation, the introduction, the methodology, the results, and some limitations that we face. And let's go to the introduction. Why intelligent systems are needed? The brief answer is that fish welfare, ecosystem health, and improved productivity can be achieved by increasing efficiency and precision of our actions. For this reason, we aim to develop tools that can be applied and connect fish behavior with husbandry practices, such as in our case, feeding. There are different technologies that can be used for fish monitoring, including eco-sounders, telemetry devices, but also cameras. The last is what we use also for our study. There are also a lot of studies that develop methodologies to analyze the videos, and they are well summarized in the recent paper of Young et al. Of 2020. Usually when the movement behavior is analyzed, there are two main methodologies that are used, group-based or individual-based. The last is the one we follow. As you can see in the first image, our videos challenge us in three parts. They are of low contrast, as the background is dark, there are nets that can impede the correct object detection, and there are occlusions. For each video frame, the first step is to pre-process the image to decrease the noise and to enhance the contrast. Next, we subtract the background, and then we use some morphological operations and some contour analysis techniques to select for the most probable fish objects. Once the objects are selected, the next step is to associate each of the detected objects between consecutive time frames. For this, a search area within a specific radius and angle view from the previous center of the fish is defined. The moving history of each object is taken into account to select between multiple objects that lay on that area, and if there is no potential object in the area, the position is predicted. Following these steps, we extract the trajectories of each fish for a finite number of time. Once a robust version of the system finished, we wanted to connect the fish behavior with husbandry practices. The questions we want to answer were: how does the fish presence on the surface and their excitation vary under different feeding scenarios? To answer the first question, we extracted the percentage of the area that was covered by the fish on the tank surface, which is, we estimated their presence at the upper layer of the tank. And to answer the second question, we extracted the instantaneous speed of the fish. We assumed that feeding affects the fish position in the tank, and we also expected that fish speed will decrease after normal feeding day, suggesting that there is an increase in the satiation. More specifically, we recorded the fish daily for 2 months, and here we will present the analysis for the last 6 weeks in May-June 2019 of our experiment. The presence on the surface was extracted for consecutive time intervals in a day, and the speed, the other variable, was extracted twice daily, once at the morning at around 8:20 and once in the afternoon at around 5:30. And we worked for 3 different husbandry or feeding scenarios. We selected Sundays, where no feeding was realized and there was no human presence. We selected Mondays, where feeding was realized after fasting and there was human presence. And we selected Wednesdays, where normal feeding was realized and there was human presence. Let's go to the results. First, we can show how successfully can our system estimate the group speed. On the left diagram, you can see how the group speed varies in time. The white dots indicate the median speed of the group, and the vertical red lines show the time at which the feeding is realized. On the right figure, the respective speed estimation using our system is shown. Our system can successfully detect sudden changes, as we can see, but is a bit less sensitive to smaller changes in speed. We shall discuss later possible improvement. The other thing we can see is that we see indeed a variation in the speed during the day, and something that suggests that we can use this variable to understand and connect it to other practices in aquaculture. Regarding the fish presence on the surface, we can see that during normal feeding days, the fish do not stay on the surface the period after feeding, and during human presence, as you see on Mondays and Wednesdays, there is a decrease in the area that is covered by the fish on the surface. However, on Sundays, the presence of the fish on the tank surface do not vary, suggesting that husbandry practices such as feeding and the human presence affect their positioning in the tank. Our observations also, human observations also, support this finding. The data I showed you before are the mean values of the multiple days. So now you can see the presence of the fish close to the surface during a single day where the variation is significantly stronger, as you can see. Regarding now the fish activity, we found that the fish decrease their speed in the afternoon after feeding is completed, suggesting that the speed could be linked to hunger or satiation levels. The figure on the right shows the bar plots of the speed for different days and for different times in a day. The asterisks, the red asterisks, indicate a statistically significant change in speed from morning to the afternoon, something that does not happen on Sundays. More data obviously are needed to be able to infer the significance of the changes on Sundays. To sum up, here, I presented a methodology that we have developed for the tracking and analysis of the fish movement. The next step includes the improvement of the fish detection using artificial intelligence, and we expect that this will improve significantly our tracking accuracy. We also showed how this methodology can be applied to link fish behavior to husbandry practices. More data and further understanding and interpretation of the data is needed. Last, we aim to apply these methodologies in sea cages. We have in fact modified the algorithm to track the fish in the sea already, and I can show you now, before I finish my presentation, an example of how this algorithm is working. As you can see, the camera is positioned at the bottom of the cage, looking upwards, and with the red dots we have the center of the mass of each fish, and the lines indicate the trajectory. There is a short tracking, so for few frames, and as you can see, the algorithm is working quite well, fairly well, for a case where the fish are not very densely packed. And with this, I will finish my presentation. Thank you very much for your attention, and I'm here for any question.